Hello everyone, welcome back to the session on electromagnetic fields. Myself Dr. Sohail Rana, and we are discussing Maxwell's equations. In last session we have discussed two Maxwell's equations related to electric and magnetic flux. So first equation was del dot D. Second equation was del dot B. Both of them used divergence theorem. Both of them are related to the densities. We have seen that del dot D is equal to rho V and del dot B is equal to 0. Both of them are based on the Gauss law. Now we will discuss Maxwell's third equation and fourth equation. Third and fourth equation are based on the cross product and Stokes theorem. So first two are related to divergence. Second two are related with Stokes theorem. So here we have del dot. So in third and fourth we will have del cross. So first one, in cross product we will take electric field intensity, and fourth one we will see the expression for magnetic field intensity. So what is their answers? That is part of our discussion. So let us begin with the third equation. Third equation is based on the Faraday's law of electromagnetic induction. So based on this topic there may be two questions. First question may be to explain the Faraday's law of electromagnetic induction and explain it in detail. Second question will be part of the Maxwell's equation. So let us revise the Faraday's laws. There are Faraday's two laws. First law states that whenever a conductor is placed in a varying magnetic field, an electromotive force is induced. If the conductor circuit is closed, a current is induced which is called as electric current. So here you can see in the diagram. On the same line, second law states that an electromagnetic induction that induces EMF in a coil which is equal to the rate of change of flux linkage. So in this diagram you can see there is a conductor with the coil wounded on itself, and it is in the proximity of the magnet. So if we move the magnet, and there will be cut off these flux lines around this conductor, we can observe that there is a production of current. Some EMF will be created, that is nothing but the voltage. This produced voltage will constitute the current. The equation which is important here, which will be the beginning of our Maxwell equation, is given by this electromotive force EMF is equal to minus N d phi by dt, where phi is magnetic flux, N is the number of coils, say 1, 2, 3, 4, 5, 6 and so on. Negative sign indicates that these flux lines opposes the direction of this current. So based on this Faraday's law, we have to derive the equations for Maxwell's third equation. So let us begin with the discussion. So we will call this equation as, say, V EMF, which is produced by the magnetic field. That is given by, say, minus N d phi by dt. For simplicity, let us consider that there is only one turn, say N is equal to 1. So what will be the expression? This expression we can write as V EMF is equal to minus of d phi by dt. Now let us focus on this phi. What is this phi? This is magnetic flux. So if we want to explore it in terms of a surface, let us imagine there is a surface, and this surface having some differential value, that is ds. So magnetic flux density is given by B. Who is the creator of magnetic flux density? The creator of magnetic flux density is flux itself. So this will be equal to the flux enclosed by this small differential surface, that is say differential phi. So we can write B is equal to d phi, this is the cos by the surface area, that is nothing but ds. So from here, if we want to find out d phi, we can write it as d phi is equal to B dot ds. So for vector field, we can write a bar on the head of vectors, so it will become d phi is equal to B bar dot ds bar. Now if we want to find out the whole flux due to the bigger surface of which this small differential surface may be part. So for the entire surface S where there is entire flux phi, we can take the integration of RHS. As it is differential surface, surface will have double integral. It will be B bar dot ds bar. So let us call it equation 1 and this is equation 2. Now if we keep this value of equation 2 phi in equation 1. So how we can modify this one? We can write the new value for V EMF, it will be equal to minus d by y dt, and in place of B we can write surface integral of B bar dot ds bar. If we take this d by dt inside, we will get a partial term. So if we can further modify this V EMF as it will be equal to say minus of closed integral surface integral, inside that we will get say dou B by dou t dot ds bar. So this is our equation number 2. Now this is expression of voltage. We want to relate it with electric field intensity. What is our ultimate task? Our ultimate task is to find out del cross E, that is curl of electric field intensity. So for that we have to somehow bring the electric field intensity term. So if you remember the basics of electric field intensity, so that I will draw here. If you remember the definition of electric field intensity, we had two definitions of electric field intensities. One is E is equal to force per charge related to the Coulomb's law. Then another one is electric field intensity is volts per distance. If we consider a current carrying conductor of differential length L, it will have a differential charge placed in that. So in that case, this expression can be written as E is equal to say V by L. For differential length, we can write it as dl. For dl, there will be differential volume. So from here, what we can say, if we want to find out the V, this V we can write as E dot dl. For vector field, we can write E bar dot dl bar. So this is differential volume. So if we want to find out the overall value of voltage, what we have to do? We have to take integration of RHS. So it will be E bar dot dl bar. So now this is another expression for voltage in the circuit. Now we'll call it as say equation number 3. So we have equation number 2, which is also voltage, EMF voltage, which is equal to minus dou B by dou t dot ds bar, and we have another expression for voltage, which is V is equal to integral of E bar dot dl bar. So if we compare expression 2 and expression 3, what we can write? We can write integral of, this is line integral of E bar dot dl bar is equal to minus surface integral of dou b by dou t dot ds. So now from here we can see that one side is line integral, another side is surface integral. So we have to make them same for comparing. So what we will do, we will take it in the form of, say we will use Stokes theorem. What is function of Stokes theorem? Stokes theorem is used to convert line integral into surface integral. So here we will write what is our last expression. Our last expression is say line integral of E bar dot dl bar is equal to surface integral of minus dou b by dou t into ds bar. Now let us call it some equation number 4. Now applying Stokes theorem so that we can make this one as surface. So if we apply Stokes theorem, what Stokes theorem says, we can convert this line integral into surface integral by taking the cross product. So we can convert line into surface by taking cross product of the vector, that is E bar. So this dl will become ds. So now we have this expression which can be compared with the RHS, which is also surface integral minus, which is minus dou b by dou t dot ds. So now if we compare and cancel the integrations from both sides and this ds from both sides, we can say that del cross E is equal to minus dou b by dou t. This is nothing but Maxwell's third equation. So if you have to write the statement of Maxwell's equation, what we can say? The curl of electric field intensity is equal to the time changing magnetic flux density, or we can say that a changing magnetic flux density creates electric field intensity. So it simply says that whenever there is magnetic field, there will be production of electric field. That is the simple Maxwell's third equation. Third one is based on the Faraday's law of induction. Now let us discuss the fourth Maxwell's equation. Fourth Maxwell's equation is based on the Ampere's circuital law. On this topic there may be two questions. One will be, it is related with the concept of displacement current and the inconsistency in Ampere's law, which was removed by Maxwell, and its derivation. So as we discussed in previous session, Maxwell has taken the earlier equations derived by the scientist. First two equations he has taken from Gauss law. Third one is based on Faraday's law of induction. Fourth one is based on Ampere's law, and he improved the Ampere's circuital law. Now in coming session we will discuss another two Maxwell's equation, and based on that there are some sub questions which may be asked. So that also we will discuss in the coming session. So thank you.